My talk today is kind of on the hardware side of supply chains. So we talk about supply chain attacks and all these things. But what we're really talking about is specific different attack vectors that are kind of focused at the hardware layer. So I'm going to talk about, gotta use a clicker. All right, so we're going to talk about the different types of hardware attacks, and then techniques assessing the different costs associated with each one, as well as access that it does provide, and how we can defend against them, if at all. So to recap on some previous some attacks that have happened in the past, so my slides differ a little bit from this, but we have the big hack that happened recently, so everyone heard about it. All right, so I was attacked by, ideally, Chinese spies reaching across many, many companies. And the idea was that they were backdoored at manufacturing time. All right, so everyone's heard about this one. And theoretically, it was easy to detect. And then earlier yesterday, we had a discussion about Shadow Hammer and Shadow Pad, different types of attacks. The ASIS one was interesting as it was actually malware, but it actually used the MAC addresses on laptops to target different types of attacks. And so this is just an example in short of what happened during this attack. And so it's still a mystery, actually, why attackers reduced the impact of their payload to only about 600 victims, even though it infected many. And then the Shadow Pad attack was interesting as it was actually targeting the update procedure behind different types of, behind different signed binaries. And then on the right-hand side here, we have Infestation, a popular video game by Point Blank. And it contains similar malware injections. It was designed by South Korean company, Zepeto company, whose digital signature was abused in this situation. This signature was actually revoked. However, Zepeto still used the certificate through the end of February of this year. All right, so now my slides are synced to this. All right, so when we're unpacking different types of hardware attacks, we're looking at the full stack, right? And it turns out we're pretty good at defending against these parts of our systems, right? We know how to encrypt data, we know how to sign binaries, we know how to put things in virtual systems or sandboxes, we know how to audit code. We can look at hypervisors and even the firmware behind it. We know how that system works. But what we really don't have a good solution for is the hardware layer. Okay, so the different types of hardware attacks that I'm going to be talking about are external standalone implants, external peripheral implants, internal peripheral implants, as well as internal implants at the chip layer. And then, of course, we have the firmware backdoors as well. So on this picture here, we see the external standalone implants. So that would be like a packet sniffer device listening on your Ethernet or Wi-Fi cables, a camera or microphone spying on your keystrokes or on your video. And on the right-hand side, we have a USB, maybe keystroke logger, physically plugged into your computer. It's a completely separate piece of hardware. And I'm sure everyone's played around with these things. Pretty low cost. However, it's very targeted, right? We have PCB implants. So, so this would be things like pictured here, where inside the chip or inside the board itself, you have a specific piece of hardware. So this is a picture of what purportedly was the Supermicro attack, where a small package or a piece was actually put on the board at a specific part on the board to leak data or to gain access to that system. All right, so, okay. And then also not pictured in these slides is the SOC or IC implants. So I actually have a picture here, but most modern processors have many, many cores inside of a single chip. So in fact, the integrated circuit or the IC chip has on cell phones especially, has everything the device needs. So it has USB, audio, video, Ethernet, memory cards, and they're all handled on one chip, not pictured here. And obviously the cost of performing this type of intentional backdoor is much higher. And more feasible technique is what was pictured previously with the Supermicro case, where you actually just put something different on the board. An example of the integrated circuit backdoor is actually the AMD backdoor, which came out, I believe, last year. But the idea was that at the IC layer, you had cheat codes in the silicon, basically. Yep, so the slides that you guys have don't have these slides. And then not pictured here as well is firmware implants. So, and that would just be like bug doors, which we'll be talking about later today about 3 for the Huawei discussion. All right, so now let's discuss techniques. But we're going to start with the Supermicro case. So that first example of this PCB implant. Okay. All right, so the big hack, right? What was it? So it was an additional microchip on the motherboard, not much bigger than a grain of rice, and it deviated completely from the original design. So it would be something that if you knew what that board should look like, it should be different. It was gray or off-white in color, and the idea was that it intercepted the CPU's temporary memory and was able to read that off and send that over the network through the chip. And they could do this because they were connected to the baseboard management controller, which is one part of that board that you would want to connect to if you wanted to get data off of it. The idea was it was a signal conditioning coupler, which is just a component. So that was the specific component they were saying it was. And it altered the operating system as well. So for the most part, all of hardware implants actually assist or facilitate a variant or a misfunction in the firmware. So there usually is a software component to it as well. And the idea was that it was embedded between PCB layers. It was thin enough where you wouldn't really notice it if you weren't looking. All right. So what's possible here? At a network level, we can use signal conditioning couplers to do memory processing or network functions. So ideally, you'd have found suspicious network activity if this case were true. Downloading firmware that's altered is also a possibility in this situation. So the Supermicro firmware could have been updated, and the malware was on the network hard drive or something like that, which would assist or be that second stage associated with the hardware implant. Built on the server's Ethernet connector to get network access. And it would appear as if it had normal functionality as well as secondary functionality. So that's what the big hack kind of shed light on. But what are other different types of these backdoors? So to explain this, we have to take a step back and look at a new wafer-level chip scaling package that came out in the past 5 years, right? So the WL CSP provides a soldering interconnect directly between a device and the motherboard of the end product. So as you can see here, this is what it would look like. Might not look like much. However, it provides the TSV, or through silicon via, which allows you to have 3D packaging. So it would contain 2 or more chips stacked vertically so they occupy less space. And this would be an example of what one would look like on the right for mobile. So you'd have different components all connected in 3D space, the result of which would mean you'd have higher bandwidth and lower energy consumption. So optimizations and saves money. So it sounds great, right? But from a security standpoint, an issue with this is that you really can't see everything that's going on. So some of these vias might actually differ, and the differences in where vias are placed might actually affect certain initial security components of the chip, or might actually connect a completely different chip that's hidden in the sandwich. And so, for example, something could be hidden right here that you wouldn't see at the surface layer. All right, so the add is a different type of technique, right? So you have the sandwich, you have the add. The ad would be what the Supermicro case was alleged to be. It'd be addition to the board. However, the issue with this is, of course, that can be a legitimate ad, right? You can move one component from one pattern to the other to save costs. You would replace a component with a different one that has similar functionality that also replaces costs. There's different package sizes available for certain things. And depending on logistics of that manufacturing plant, only certain ones might be in stock. However, this would differ from the original spec. However, it's become almost prevalent across different manufacturing firms that these replacements do happen. All right, and so you can also have an ad inside of a package. So you'd have different flash memory packages, as you see in the picture here. There was actually different 3D bonding patterns on this chip. Now, the reason for this was they actually used it for many different types of boards. So they'll swap out different subcomponents that have multiple functionality and then just not solder different vias into the board. And they do that so they can reduce costs, increase the time from start to finish, that sort of thing. All right, so this is a picture of Trammell Hudson's example of what he would do for a hardware implant. He swapped a component on a device. This is just one example of one thing you could swap. And this would mean that the board would function as usual, except it would have a different functionality. They were able to flip ones to zeros in flash memory using this swap. And it could alter enough data such that when you connected to it or when the firmware ran on it, you could actually get command execution. All right, so PCB or die level attacks. This hasn't really been discussed much except in academia. However, it is possible. And that would just be an addition to the actual silicon of the PCB. So it would be very hard to detect. These things are really small, so you'd actually have to use micro Sophie on a decap chip. And again, this can be done inside of a legitimate processor at foundry time. All right, so one thing I joke about is, every hardware talk, you can know it's a hardware talk by the fact that all the pictures in the slides are not actually screenshots, but these are pictures of the different stages of manufacturing time. And so, allegedly, the manufacturing plants claim that at each stage there are checks such that if there were these back doors put in place, they would know about it, right? Because of all these different tests that happen. And for the most part, that is true. So it'd be very difficult for an unsuspecting manufacturing plant to actually have someone put a malicious back door in at any of these stages, once the designs have been approved of. Okay. Okay, so what's the most likely attack? So in general, counterfeit or e-waste parts are often used to shave costs off of manufacturing time. This is probably the most likely scenario of lowest cost. It's the largest risk to firms, so maybe it's not even a security or a backdoor that's put in, but it alters the design of the board such that it reduces the security of the design. And so to prove intentionality is a different problem entirely. Okay, so like for example, in Bunny's example of engineering on FPGAs, the most likely a type of attack would be these e-waste parts. And why does money talk here? A distributor makes about 3 to 5% off of a chip. So if they can inject 3 to 5% of fake chips in there also, they would actually double their profits. Just because in engineering, costs are so high that profit's pretty low. So these are actually from the Supermicro boards here, different components that actually didn't match the ones in the specification. However, they're different models of the same thing. So the idea that we assumed was it was just a cost reduction. Now, to defend against this is pretty difficult too. You'd have to have a representative in that factory verifying that each board has the approved of of components on the board. So it's pretty unlikely that you'd actually do that. All right. So another example of the cost here is just Bunny's numbers that he used in his talk earlier this year, where he was saying that it would really cost in the low 10K for wire-bound implants to happen, and the mid 100K for that WLCSP, that 3D chip packaging implant. So it's much cheaper to actually just change out a component. All right, so this is just kind of laying out the different types of hardware attacks and what we consider to be easy attacks to perform and easy to detect. So obviously the add component one, you'd be able to know for sure if that was different. However, the substituting the component one is actually quite hard. So with Trammell's example, where it was an active component, you'd actually have to do additional analysis to determine if, for example, a passive component on the board was actually active, if it differed enough from the specification of the board to cause problems in your design, that sort of thing. Now, in my opinion at least, editing the IP list at before manufacturing time actually starts, so editing the silicon design, the RTL files, which are actually these kind of DLLs that are loaded in at manufacturing to help design the silicon parts of the chip. If you can edit those, then you would actually have pretty low cost, but pretty hard to perform modification to all these chips. So the example of that would be ARM. So everyone knows that ARM makes their money because they license their RTL files, right? They license them out, people take those files, they put them in a CAD program or something, and they print that silicon into the chip, and now they have ARM. But in that situation, if the design actually has a specific problem in that file, or certain commands that really shouldn't be there, then that would affect everyone. It'd be very hard to detect. It would be very prolific. And that was the example with the AMD cheat code hack that came out earlier this year. All right, so how do we defend against this, though, right? So we have all these different types of hardware implants. We want to look at the board and say, this is perfectly good or not. Now, one thing that people are playing with is before fab time, the actual RTL or the silicon design of the chip can actually be formally verified. So companies like Galois are creating tooling to allow you to say, this circuit design is 100% secure, or this circuit does exactly this. Nothing more, nothing less. And that's one way to lock down the silicon of the chip. However, if you have your board already, what would you go about doing? So, just going through all my transitions here. Okay, so you'd have to assess your security hygiene. So no matter what, even if your boards are backdoored, if you don't have good corporate security in general, then it doesn't really matter. There's no need for the hardware backdoor anyway. They're probably already on your system. But then also you'd have to assess your supply chain risk. So one thing that Supermicro, didn't have going for it was they actually outsource their manufacturing to a third party in Taiwan, I think, and they actually outsource different parts of the manufacturing to other sub-companies as well. And so at that point, it's becoming a larger and larger problem and harder to lock down. And so at every point in that process, something could happen to alter the design in a way that's undetectable. And so also, obviously you have to focus on different areas of your manufacturing. So you have to look at the code, the build system, programming, hardware. There's a lot of different components of a good chip. And so one quote from the UK, this report on Huawei, was, they said we couldn't really determine intentionality for any of these bugs in the chip or in the software. But these findings were just about basic engineering competence in cybersecurity hygiene. And so in this situation, There could be bug doors. It could be just really bad. But the fact that a lot of these problems with the design at all layers that weren't addressed was really the critical part here. All right, so supply chain. If you try and break it down into the different components of assessment, this is kind of the line that I like using. You have the software and hardware components that eventually merge. So after the boards are made, it's shipped somewhere else, and the code is actually flashed onto the chip. So the first stage, of course, security. All right. The first stage, you want to look at specification of the actual hardware and software of the board. So you develop a specification. Usually that's done in-house. For Supermicro, that was done in California. And that can be easily checked. So you have one specification, one RTL file for the silicon, formally verify or go through and just code review. This can be easily checked for backdoors or other failings in-house. Now this is the easiest time to insert a low-level hardware backdoor if you do control this process, right? So if you controlled everything, the manufacturing, you could say, okay, we'll just insert a backdoor here. It's cheap, it's easy, everyone's happy. However, in stage 2, you start to reduce the specification and design to practice. So you'd start to go through and look and say, well, we've had these bits of code in here forever, as was the case with Supermicro. They actually used libraries from like the 90s in some of their firmware development. And so you'd have to say, well, we haven't looked at this in a while, let's go through it. And so like 3, 4, and 5 just labeled here. Manufacturing, on the other hand, happens through a third party, so it's not as hard to detect. So that would be the product line, programming, provisioning. That's all done out of house. In the hardware integration as well. So at all of these stages here, it's kind of out of your hands for the most part. And so by the time you get to the distribution channels, in the warehouse or in transit to the customer, the company and the customer has less ability to claim the device matches the specification. So around stages 2, 4, and 5, you start to lose control of what that specification looks like. And you lose the ability to actually check easily if it does match. And then finally, obviously, it's installed in the system. And defense really depends entirely on the customer. So once it's installed in Amazon servers or something, Supermicro can't actually easily help them out at all. Now, attacks are possible at 6 and 7. So distribution, obviously, you don't know who's shipping your stuff where, or what's being done to it in that process. However, we're not really going to talk about that much today. Okay, so Supermicro claimed a lot of the R&D happened in-house, which it did. They were using code from the 90s, but it was still done in-house. They still had the ability to go through and check the design of the hardware, the silicon, everything. However, they contracted out to a large supply chain, and they had a lot of customers. So Ablecom Technologies, which is Taiwanese company that I mentioned, is actually run by the Supermicro CEO's brother, which I thought was funny. And they actually only offer warehousing and coordination. So they're the ones who manufacture the device, but in fact, they don't do any of the manufacturing. And they take up 15% of the cost of sales. So they have a pretty big stake in the company's success, in the success of the chip. And they basically do warehousing accuracy and forecasts. So they determine where different parts are and where the best place to manufacture certain components are at that given time. All right, so kind of stepping through this again, Supermicro designs it, Ablemicro coordinates, contract manufacturers produce and actually do the shipments, and they ship to San Jose, Netherlands, or Taiwan for final assembly. So final assembly of all the parts and the flashing of the firmware actually happens in only 3 locations. And then they obviously go through distributor to customer. All right, so late last year, we were given the task of looking at some of these boards. And so we sat down, we had some boards in front of us, and we're like, okay, well, it's gray or off-white in color. we're looking for maybe a signal conditioning coupler, who really knows. Um, and we're looking for things that are unlikely to be detected without specialized equipment, so something that probably has that hidden behavior. However, this is a very poor description, and so actually just basing it off this was impossible. So we started to simply look at everything, and that was the answer for most of these problems. All right, so first thing you can do when you're just looking at the board is follow traces on the board, trying to reverse out the net list that's actually physically in front of you and compare that against the net list from the Supermicro design spec. A net list, for those who don't know, is just basically a map of components on the board and how they connect to each other. And so obviously this takes a lot of time. It's visually time consuming, and it requires expert knowledge of how these things connect. Now, electrical testing is useful for the cases where components are actually active versus passive. So that would just be components that maybe look the same, but they actually do processing of the different bits that are going through them instead of just passively passing them on. All right, so how are we going to look for the add here? Well, you can try X-rays. So if you have an IC, you can look through it with an X-ray, because just looking at it from the top level actually doesn't tell you much. This is pretty destructive as well. This is just a picture of the different parts of the chip. So as you see here, the top part, that looks pretty normal. It matches the picture we saw a few slides ago. However, if you look at it from the side, there's different layers to this integrated circuit, and each layer has the potential to be slightly different or to have slightly different functionality based on how it's connected. And so that actually means you have to start delayering this integrated circuit. Additionally, you can use X-rays to detect passive versus active, like I was talking about earlier. So here on the right, we see the X-ray of a board. This isn't a Supermicro board, but same idea. Usually these boards are much more complicated than this. This is pretty simple. So you'd have maybe thousands of different components in this X-ray that you're actually looking for active components. So we have the resistor, which is just passive, capacitor on the upper right-hand side. And then we actually have that chip, which is active, or the inductor inside of this DIP package, which is pretty interesting. However, this also is pretty destructive to the board, and it requires removal of the components. So the real problem with this is that you can't do this on all of the boards that you get in the shipment, right? So you get in a bunch of boards. Maybe you can test one this way, but there's no reason to claim that if you prove one's good and correct, that it actually means that all of them are. All right, so specifically for the Supermicro assessment, we ended up looking at a lot of X-ray images. You have to do about 500 per PCB just to get the actual full image of what's going on inside, and get all the port details and stuff. So a lot of images to look through, and unfortunately there's no real automated tooling for this. So one idea that I think is kind of in research stages now is to actually use OpenCV or something like that to process all of these images of the board itself, so maybe pull off that net list, or of these X-rays to pull off the different interconnects between the layers, and maybe match that against a known good PCB X-ray. All right, so each person that was operating these X-rays had 5 to 10 years of experience in electronics, and had to analyze the image twice for it. This is just kind of showing that it is pretty difficult to do this sort of analysis, following different wires and connects and things like that. And you end up with a huge tub of SMD parts from the motherboard. Oh. All right. So going back to our earlier example, because the Supermicro backdoor was allegedly on the bus, not the SPI, you can't read flash, watch the SPI bus by clipping onto that SPI chip, or replace the SPI chip because it probably won't actually help in this situation. So this is pictures from Trammell Hudson's talk at CCC, which shows the different types of ways that people would try to detect his implant, but it wouldn't actually work, just given the location of it. All right, so that's all the hardware stuff, right? But who cares about codes? Who cares about code in these sort of supply chain attacks? And so in this specific example, there was a firmware update that actually also distributed malware as well. All right, so this is what kind of one thing I mentioned earlier, but one thing to reiterate is all hardware implants don't operate alone. They probably can. However, if you actually want a successful, useful tool that's implanted onto the board, you'll actually have to have a software component here. And so what do you do with that, right? So how do you check that the software isn't actually abusing or using a misprint or a incorrectness in that board? And so, you can check your code at compile time, look at the build system, reverse engineer the firmware that you pull from the board, which is what we did with Supermicro. However, as the UK's report on Huawei says, it's not possible to be confident that source code actually matches what's on any specific board at a specific time. So it might actually match what's on the board immediately, but after an update or two, it could be completely different. All right, so obviously different steps that you could do this. Source code, which would be those bug doors, which is what the UK was trying to do to look at Huawei. You could look at compiled firmware, which is what we were doing for Supermicro. And even though you might not have the original firmware, you can look at boards across different time periods to see if the firmware deviates at all significantly at specific parts of the process. So normally, they're not going to change parts of firmware that interact directly with a component that's been there forever. So if you see a change in that, that's a red flag. Sorry. So, and also at the chip layer, differences in lower high bits actually matter a lot for firmware at different parts. So looking at that as well. Yeah. All right. So other things to look at that I'm not going to go into depth with, and what we would have done if we had continued on the Supermicro stuff is look at once it's turned on, is there any RF components to its operation or any network anomalies that can be detected, do the network or RF outputs differ at all from previous Supermicro boards? All right, so possible solutions. There you go. Computer vision, machine learning. No, I do think that there's more room to be done on automating the reverse engineering process of these IC components as well as the actual board itself. So one thing that I really do want to see is better tooling around lifting netlist off boards, looking at the integrated circuit connects. We need the ability to automatically trace or compare lifted netlists or X-rays between each other. And obviously these are destructive, and you can't apply security. You can't apply security results from one board to the other, but it would actually help a lot in this domain, as most of it's very, very manual right now. All right, so that's my talk. Are there any questions?